So in this section, we'll look at how we can use the second derivative to determine another key feature of a function's behavior known as concavity, a topic of 3.2. So concavity and the conditions for what it means for something to be concavity. So concavity describes essentially how a graph curves or opens up. So concave up would mean that our graph curves upward like this and opens upward, while concave down means that our graph would curve downward and open downward over a certain interval. The point at which a graph changes concavity from either concave up to down or vice versa is what we call an inflection point. Seen right here in graph. So we're going to develop the conditions for concavity by looking at two very simple functions, the parabolic function x squared and its reflection across the x-axis, negative x squared. The reason being is that both these functions are either concave up or strictly concave down, so whatever conditions we develop for one or the other is going to hold in general for all of concavity. So if we look at the graph of y equals x squared, and we take the second derivative of y equals x squared, we're going to get y, the second derivative equals 2. Now if we take the reflection across the x-axis, y equals negative x squared, and take the second derivative, we're going to get negative 2 for our second derivative. This forms the conditions for concavity of a function at a specific point. Specifically, we notice that the second derivative is positive for a function that's always concave up, and the second derivative is negative for functions always concave down. So using these conditions, we can note that if a function is concave up at x equals a more general function, not just the quadratic functions, then its second derivative at that point is going to be positive, greater than 0. While if a function is concave down at x equals a, that signifies that its second derivative is going to be less than 0 at x equals a. So these are our two conditions that we need for concavity. So in order to determine concavity, we apply a test that's similar to the first derivative test, except now we rely on the second derivative. So what we're going to do here is we're going to determine the second derivative of our function f. We're going to set the second derivative equal to 0 to solve for the candidate inflection points. We call these candidate inflection points because they may or may not be inflection points based on whether or not the sign of the second derivative changes at the specific point. So in addition, we also look for x values where derivative does not exist. As we've seen, this occurs again mostly with the quotient rule. So the candidate inflection points are going to be where our second derivative is equal to 0 or does not exist. In between each candidate inflection point, we're going to evaluate the second derivative to determine the sign of the second derivative over the interval. Again, so this is similar to the first derivative test, except now we're using a second derivative instead to apply it to concavity. So second derivatives are always associated with concavity, whereas first derivatives are always associated with increasing and decreasing intervals. So next we're going to interpret our results. So same thing as we did with the first derivative test, is that if we get our second derivative of a point is greater than 0 in between critical points, or excuse me, inflection points, that signifies that f is concave up over that interval. So let's look at an example here, applying the conditions for concavity. Determine the condition or the concavity of the function f of x equals 6x cubed minus 4x squared over the entirety of its domain. So what we end up doing here is we're going to take the second derivative. So our first derivative of 6x cubed minus 4x squared is going to be 18x squared minus 8x. And then as a result, the second derivative of that will be 36x minus 8. So now what we're going to do is we're going to set 36x minus 8 equal to 0 and solve for our possible inflection points. Again, this is another polynomial, so we see that we're not going to have any division by 0, so there aren't going to be any points where our second derivative does not exist. So solving this equation right here yields a candidate of 2x equals 2/9. Had a little bit of a brain fart there. Want to make sure I did that problem right. So now what we can do is we can set up a number line right here, just as we did with the first derivative test, where we have x equals 2/9 as our possible inflection point, and then we use test points for x less than 2/9 and x greater than 2/9 to determine the concavity of our function. So we see for x equals 0, aka a test point for less than 2/9, we're going to get that our second derivative is less than 0, while for x equals 1, we're going to get that our second derivative is greater than 0. signified right here by the negative sign for x less than 2/9 and the positive sign for x greater than 2/9. So what that indicates to us is that f is concave down from negative infinity to x equals 2/9 because our second derivative is less than 0 over this interval, while f is concave up over 2/9 to positive infinity as our second derivative is greater than 0 over this interval. So we can see it's just like the first derivative test, except we cannot confuse the applications of the first derivative and the second derivative. First derivative, again, I can't emphasize this enough, is strictly with the increasing and decreasing intervals. Second derivative is always associated with concavity of a function. And then lastly, we can see that f has an inflection point x equals 2/9, not only because the second derivative is equal to 0, but we also have to check that second requirement, that it changes signs, and that does in fact occur at x equals 2/9. So, determining concavity from first derivative graphs. So just as we can use the first derivative graph to determine increasing and decreasing, we can also use concavity. We can also use the first derivative graph to determine the concavity of an original function f. So, the idea goes as follows: is that the derivative of the first derivative is the second derivative. So, if we're given the graph of a first derivative, that means the slope of the tangent line to the graph of our first derivative is going to be the second derivative at that point. So here's my curve of the first derivative. The slope of the tangent line at x equals x naught of this curve is going to be the second derivative. So what that tells us is that if f prime is increasing at x equals a, then our second derivative is going to be greater than 0 and f is concave up at x equals a. If our derivative is decreasing at x equals a, then that indicates that our slope of the tangent line at that point is going to be negative, and hence the second derivative will be less than 0 at that point. So as a result, f will be concave down at x equals a. If our first derivative has a local extrema at x equals a, then that's going to indicate that the slope of our tangent line to the first derivative is 0, and thus that our second derivative at that point is equal to 0. And as a result, if we see that our second derivative changes signs, aka the first derivative goes from increasing to decreasing, or vice versa, f will have an inflection point at x equals a. And again, I can't emphasize this enough. This all goes back to the idea that the slope of the tangent line to our graph of first derivative is nothing more than our second derivative at that specific point. So let's take a look at an expertly drawn curve right here of a first derivative to see how we can apply this. So we see right here we're going to have two possible inflection points: x equals a and x equals b. Okay. So what we can see right here is that our first derivative is increasing from negative infinity to x equals a, and also from b to positive infinity. So that indicates the slope of our tangent line to the first derivative is positive over those points, and hence the second derivative is positive over those intervals, from negative infinity to a and b to positive infinity. Next, we notice between a and b, we notice that our first derivative is decreasing, which indicates to us that the graph of the slope of the tangent line is negative over that interval, and hence the second derivative over the interval ab is less than 0. As we can see right here, we draw the slope of the tangent line right here. We see that the slope is negative when the first derivative is decreasing, indicating to us that the second derivative is less than 0 between this interval. So now we can see that our first derivative has local extrema and thus inflection points at x equals a and b, because we see when we graph the tangent line here, we get horizontal tangent lines at x equals a and x equals b. Horizontal tangent lines, again, for our first derivative curve tells us our second derivative at these points is equal to 0. So if we organize the results in a chart again, we can see that for x between negative infinity and a, our second derivative is positive. We see that x equals a, our second derivative is equal to 0. And we see that for x between a and b, our second derivative is negative. We see that for x equals b, we're going to get 0 for our second derivative. And then for b to positive infinity, our second derivative is positive. So that tells us as a result that f is concave up from negative infinity to a and b to positive infinity as our second derivative is greater than 0 over these intervals. F is concave down over a to b as f prime of x, as our second derivative is less than 0 over these intervals. And f has inflection points at x equals a and b as the second derivative not only equals 0 but also changes signs at these points. Again, the first derivative graph is a little bit trickier to work with, so we'll spend some time with this in class to make sure we have this really hammered down right here. Lastly, we look at the second derivative test for local extrema. So if we have a function that we know nothing else about besides its value as the value of its derivative at a specific point, we can use the second derivative test instead of the first derivative test to determine whether we have local max, local min, or neither at the points. The logic goes as follows. If there's a local maximum, let's say at x equals a right here, okay, we notice that there's not only a horizontal tangent line, but also that our graph is concave down. So the first derivative will be equal to 0, and the second derivative will be less than 0. If we look at a local minimum right here, we can see that we have a horizontal tangent line and that our graph is concave up. It opens upward. So as a result, our first derivative will be equal to 0, and our second derivative will be greater than 0 when we have a local minimum at a specific point. So at x equals a, summarize our conditions. When we have a local maximum, the first derivative will be equal to 0, indicating us a horizontal tangent line, and the second derivative will be less than 0, indicating to us a local maximum, or a concave down part. And then for local minimum, again we have a horizontal tangent line, but now we also have the condition, and this is actually a typo, that our second derivative must be greater than 0, so put a greater than sign right here, not less than. Our second derivative must be greater than 0, in order to ensure the concave up portion of our requirements seen to be above bullet points. Please note that both these conditions must be met for a local minimum or maximum to occur. So if we have a concave up region but not a horizontal tangent line, then we don't have a local minimum at x equals a. And these summarize our conditions for how we can apply concavity to a function. We'll apply a second derivative test to problems in class tomorrow as a collaborative effort.